All right. Quiz tomorrow. So we'll run through quick review here of things. We can talk about what's on it anyway. See what questions you have on limits, because that's probably a big part of the quiz for sure. And we probably need have the most questions about it practice. I've got a worksheet here with some limit practice, about 8 problems. I've got a Newton's Law of Cooling on there, and so forth, so you can work on that or whatever you need to work on. Chemistry, maybe. But obviously, we work on the worksheet, the review for the quiz, those kind of things. But if you've got, practice your calculus carols or something, I don't know, remember we got that on Friday. Okay? And we'll have to get right in here and get going, because then they're going to cut in the third block of things. So we're going to have about a half hour, so we'll get our calc carols going right away. All right, so on the quiz, 4.1 was about the slope field, so you're going to have to do some matching. I don't have any new problems to do on that, but I do have the this one worksheet here, the answer key up here, if you never did get a check, how you did on that matching and so forth on that worksheet, so you can look at that. We also had some matching in the book. That other worksheet we did with the calculator document had some matching too, so we've had quite a bit of practice on that. So if you've got some questions, like I said, this should maybe take us a half hour or so. You probably have a good hour of work time here today and review. So if you've got some questions on the slope fields, matching those, whatever, be sure and come talk to me at some point along the way. Also, drawing slope fields like on this page, maybe it would be 1 or 2 or 3 little ones to draw, or maybe just one big one to draw. And then also I had sketched in, now I don't think I told you to do that on this worksheet, but I think one year I had told the class, use the initial condition 0, 1 and sketch in the solution curve. So I think that's what's the reason I have some solution curves drawn in on this worksheet here, if you're checking that. So you need to be able to do that too. So if I give you a slope field or have you draw a slope field and have an initial condition for you, you should go with the flow, be able to draw your solution curve in there. So that's those first 3. Match slope fields, draw slope fields, and then sketch your solution curve. And then be able to work with Newton's Law of Cooling. Okay? And there's one on the worksheet here, number 23, number 24 in the book, that Boris and Natasha problem. So work just like that. You need to be able to do that. Okay? Somebody asked about the calculator, no calculator, it's both parts. The calculator part's shorter. The calculator part's basically just the Newton's Law of Cooling, okay, situation where you want to be able to solve for that. And then maybe where you draw the slope fields, like this, maybe I'll let you use your calculator for that in case you add some numbers or divide some numbers or whatever you want to use. It shouldn't need it, to be honest with you. Your calculators can draw a slope field, but it doesn't really help you if you're having to draw one by hand, because by hand you have to draw the slopes at certain points. And when you draw a slope field on your calculator, it draws them kind of randomly. It doesn't draw them at the same points you'd be drawing. So that wouldn't really help you there anyway. So really all the calculators can be used for is solving that exponential when you're doing Newton's Law of Cooling. All right. Then the rest of the quiz is no calculator, and that'd be all the matching of the slope fields and all the limit problems. So more than half of the quiz is no calculator. Okay, and so we got the stuff with limits. It was section 4.2. Okay, so just to review the limit things, this is what I had up here yesterday. So we've got 2 basic types of limits. Limit as x approaches a number. Limit as x approaches infinity. 3 basic things can happen. Either you just get a number, you plug in whatever, you just get an answer. That's your limit. Or you get one of these things. Now, we were having the discussion here earlier. Infinity over infinity is not 1. 0 over 0 is not 1. It might come out to be 1, but that would be just luck, right? I mean, it could be 2, it could be 3, it could be 1/3, it could be does not exist, it could be 0, it could be anything. Okay? Infinity over infinity is not 1 most of the time. I mean, it may come out to be 1, but that's just because it could come out to be anything. Okay? So, and the question was asked earlier because second block, one of the problems on your worksheet comes out negative infinity over infinity, and the answer comes out to be -1. That's coincidence. okay? It's not -1 because it was negative infinity over infinity. All right, what that means, it's indeterminate. We can keep going. Now, let's just do a quick example here of what we mean by that. So when we learned L'Hopital's rule, so what I've got here is I said you keep going. Maybe a factor, do a least common denominator, do a conjugate, do L'Hopital's rule. Just ask yourself, which is growing fastest? Something. If you get 0 over 0, infinity over infinity, or 0 times infinity, you have to do some more stuff, and you might get an answer. The limit might exist, or the limit might not exist. And you do one of these two things. But this middle section, that's the key. So one that I just think of right off the top of my head is one like this. Limit as x approaches 2, right? So you plug a 2 in and you get what? 0 over 0. So what's that mean? That means you keep going. Now you do one of these things. You can do any of these things, right? Now, which is growing fastest? That doesn't really work here. 0 over 0 means they're both getting small. Which one's getting small fastest? Well, turns out that there isn't really one that's getting small faster by anything. So that wouldn't work. But we could do L'Hopital's rule, but we could also do this. Many of you would probably think the factor. That's what we would have done, a week ago before we learned about L'Hopital's rule, or even 2 days ago. We'd have done this. We'd have plugged in a 2 then, and we'd have got 1/4. And you can still do that. So if there's one like that in the quiz tomorrow, do that. That's great. Okay? Or, since we've learned L'Hopital's rule, we could do the derivative of the top, which is 1. And the reason we could do L'Hopital's rule is because this is 0 over 0. So derivative of the top is 1. What's the derivative of the bottom? 2x. Now we put our 2 in. 1/4. Either one of those. I don't care. Now, I would encourage you to show your work. I would encourage you to write this down or write that down, although I'm not going to be that picky about it, but there will be some problem. The default position for the AP test is to, if you're not sure, show work. Show work. Okay? They say in the directions on the AP test, and they talk about bald answers. Bald answers oftentimes do not receive credit without some sort of work justifying what you're doing. Okay? So if you're unsure whether you need to put any work down, put work down. Okay? Now, there may be some, there's one on the worksheet that I'll talk about after I've given you a chance to look at it and talk about it. So at the very end of the period, I'll talk about it. But that's one where I would definitely take off if you had an answer like that -1 we were talking about. Negative infinity over infinity, and you wrote down -1, didn't have any other work. I would assume that you thought negative infinity over infinity is -1. Infinity stands it. Without some supporting work there, which on that problem you definitely would need. Okay, could you have done some of this in your head maybe? I would think so. A lot of you could just do that in your head, I'm guessing. Right? But write it down. Write it down, I think, to be safe most of the time. Okay, so back to our notes. So anyway, this L'Hopital's rule is just one tool that we can use on some problems, but we can do other stuff on some problems. So here's be another one. Right off the top of my head, think of one we've done. X goes to infinity, x squared over 2 to the x. Now here's one I don't think there'd have to be any supporting work on this one at all. What is the answer to this one? The answer is 0. Why? Yeah, the bottom grows faster than the top. And so that's going to be a 0. Okay, so now it certainly wouldn't hurt to write that out if you wanted to, but I don't think you have to do that. When I talk about showing work, I'm not really asking to explain in words on any of these, although if you want to throw some of that down, then it never hurts. But I'm not saying that. I'm saying some mathematical kind of work. Now, on the does not exist, of course, we do have to kind of show why. Now, a lot of times that's our work. A lot of times it's this right here. Check both sides. Right? If you get 7 over 0 or 11 over 0 or something when you plug in, that's usually a vertical asymptote situation. And so the limit does not exist. Why? Well, that's where you check the left and the right, and you mention why it doesn't exist. Okay? And that's your work showing that. So you might have to, if it's x approaches 2, you might have to plug in a 1.999, a 2.001, and show that you're getting infinity or negative infinity in those vertical asymptote situations. Also, some that don't exist is because the limit gets bigger and bigger and bigger. If I take this one I did here and flip that around, if I had this, I think this is actually the one we had in our homework. Right? What's that limit? Does not exist. infinity, right? Because here the top is getting way bigger than the bottom, so there's nothing really to show there. You're telling why it does not exist by writing infinity, okay? But another way you have to tell why it doesn't exist is checking the left and the right. Of course, you can't check the left and the right on an infinity, right? You can't be left and right in infinity. All right, so those are it. I mean, that's the stuff. That's the stuff we got to do with limits. Now, we need to see that in action on some of these problems, but that's what we're talking about, okay? And that's what we need for the test. All right, homework question. Let's start. I tell you what, before you guys ask any, let's just start with 42 because I saw some issues with some people on there. On 42, this is this graphing one. So, this is a little different. And you know how the quizzes go. Sometimes there's a question that's a little different than any of the homework ones we've had, but it makes you pull together the information we've been learning. And 42 would be a good one like that. And there could be some other ones too. Most of this quiz is not tricky at all. It's very much like the things we've been doing, but you could always expect something that's maybe a little out of the ordinary. Okay, so on this one, you're supposed to draw a graph of a possible function f that meets these criteria. Okay, what was the first one? -3 to infinity. So, all right, something about domain. So we're not going to go left of -3. All right, what else? Range is -infinity to 2. So this graph will not go above 2. Right? All right, what else does it say? So f of 5 equals 0, f of 0 equals 0, and f of -1 equals 0. So this graph is going to go through those points right there. Okay, what else did it say? Have a limit in there. So if we approach -3 from the right, okay, so that's going to be a vertical asymptote, right? So it means this graph's going to kind of go down like that. Okay, so I'm just kind of putting the pieces together here. Then what? It says something about x approaches 2, -3. So the limit as x approaches 2 is -3. Now what's that tell me? Is there a point there? Is that what that's telling me? No, that'd be f of 2 equals -3, right? If there's a point there. Okay. Then it doesn't just mean the cars meet there. So there's a line. So could it be an open circle there? Could it be filled in? Yeah. It could be filled in. It could not be filled in, right? The cars meet there. Maybe the diner's there. Maybe the diner burned down, whatever. But that means that, there's, somebody said a line there. It could be coming through like that or whatever, right? The cars have to meet there. That's what we know is going on. Okay, so it could be filled in, maybe not filled in, whatever. But we know something's going on there. It might, okay. So I'm not even going to, until I get the rest of it, I'm not going to even put anything there. I know I'll put a dot there. What the heck? There's no reason to have it open, but there's something going on there. All right, what else did it say? So as x approaches infinity, so that means way out here, we got a horizontal asymptote at 2, right? X is approaching 2. Now remember, we said with a horizontal asymptote, it's okay to cross a horizontal asymptote. So could we go up here and then come back down and kind of do that? In this problem, no. Why? Because the range is limited from -infinity to 2. So we cannot go above 2 because of the range. But the horizontal asymptote part, right, as x approaches infinity, So a horizontal asymptote, we could do that, or we could just go up and then come back down to 2 from the top side, whatever. Those could all happen because of that infinity thing. But since they told us the range is up to 2, we can't go above that, then we would have to stay below that line. Okay, that's all we need. All we need is to hit those points, and that'll do it. So this was come down here, so this would go up. Now, it doesn't have to go up. I mean, I could have this point come up and then back down and then through there, right? I mean, it doesn't tell me what's going on in between there. So you guys have some different, you can have some variety to your answers. You could just come right up here and cross there, as many of you did. I noticed when I was looking at it. But whatever, it doesn't say that it can't be 0 there, it can't be 0 some other places. It just said these are the places where the function is 0. But it didn't say there couldn't be any other. Okay, so anyway, so that's there. And then we said this has to come through. It could be a minimum. That could be a local minimum, but we don't know that, right? All we know is the cars meet at this point. So I could make it a minimum, and again, this could go here and here, whatever. We don't know, but we know it has to go through there. And then we know it's got to level off up here, like that, right? So this would be an okay answer to that. This meets all those criteria. Now I could have an open circle here, that'd be okay, because the cars would still meet, so that would take care of that limit. We got our negative infinity, so that takes care of this limit from the right. Got a horizontal asymptote, that takes care of that one. The range, the domain's all good, right? So, be able to put those things together to answer those questions, a question like that. All right, now let's look at some limit problems. Somebody got one that they want to talk about? There's some good ones on there. 65. What's that one say? All right, so the first thing we do is plug a 0 in. So cosine squared is really cosine and then squared. So cosine of 0 is 1. 1 squared is 1. 1 minus 1 is 0. The bottom we have 0, so this is 0 over 0. Oh, so that must be 1. No, good. I was looking to see if anybody was shaking their head here. You could. 1 minus cosine squared is sine squared. Now that might be useful, sort of. It's still 0 over 0 though, right? So that doesn't help that, but as far as, that's perfectly fine to do that or not do it. Actually, it's not going to matter either way here. So what do we want to do? Well, we look back at our notes and it was, well, you get 0 over 0, you can keep going, some sort of factor and cancel kind of thing. We have L'Hopital's rule, what's growing the fastest, right? Those are kind of some of the options we had. Well, if I look at this, I can't really tell how fast these are growing necessarily, so that doesn't, well, not growing, they're actually getting smaller. Can't really tell which one's getting small fastest, that doesn't work. Factoring, canceling doesn't work. Really, L'Hopital's rule is what I got, right? So, derivative of the top. Now, how do we do the derivative of sine squared? Right? Isn't that sine squared? So, it's a derivative. 2 sine times cosine, right? And the derivative of the bottom is 2x, right? Because remember, you got to do the derivative of the outside, so you bring the 2 down in front, you leave the inside alone. Some of you taking the gateway test, and some of you maybe who even passed the gateway test and drive me crazy. With the chain rule, you're doing the derivative outside, and then you're doing the derivative inside. You don't do that. You leave the inside alone. So you bring the 2 down front, leave the sign there to the first, then you times by derivative inside, which is cosine. Okay? If I could tell you the number of people on the gateway test that are doing this, like if I give you this, something like this, then they're putting a 5 down in front, then they're putting 6x on the inside and then to the 4. Right? They're doing the outside and the inside all at the same time. That's not the way it works. You leave the inside alone. All right. So, now we plug in a 0. We get 0 over 0 still. Do it again. Except now we got to do a product rule. That stinks. Cancel those 2's. That'll help a little. Okay? Do a product rule. Derivative of sine is cosine. Leave the cosine alone. Which would actually make that cosine squared. Plus, leave the sine alone. Do the derivative of cosine, which is negative sine. All over the derivative of the bottom, which would be 2. Now we put under 0. Cosine. It would be 1. Forgot. So I wrote an x. It would be 1. That's right. We canceled the 2. Okay? Derivative of x is 1. All right. Cosine of 0. Now we plug in a 0. Cosine of 0 is 1 times 1. Sine of 0 is 0 times 0. 1 minus 0 is 1. 1 over 1 is 1. Oh, look at that. 0 over 0 is 1. Sure, but 0 over 0 could be a lot of things. But it turned out this time it was 1. Okay? Coincidence. Coincidence, coincidence. All right. Another one. 71. Limit. What is it? Okay. Yeah. So I guess it doesn't really make. Yeah. We'll write it that way, but it could be pi halves x or whatever. So and then what's on the bottom? Sine of pi x. All right. So we put in a 1, so that would be cosine of pi halves, which is 0, right? Cosine of pi halves is 0, cubed is 0, and then put in a 1 for x here, we get sine of pi, which is also 0. So we get 0 over 0. So we have to do, don't have to, but that's probably the only thing that's going to work here, so I guess we do have to, is L'Hopital's rule, right? L'Hopital's rule, especially when we get into these ones with sines and cosines and, the trig stuff. And yes, we have to be able to do that. Okay, so what do we got? Well, we got this is all cubed, cosine all cubed, right? Like that. So we got to bring the 3 down in front. Leave the cosine pi x over 2 alone. Squared times the derivative inside, which would be negative sine pi x over 2 times the derivative of that inside. What's the derivative of pi x over 2? Pi x over 2 is just pi halves x. So what's the derivative of that? Pi half. So that's all the derivative of the top. Times the derivative of the bottom, which would be derivative of the outside, cosine, leave the pi x alone, times the derivative inside, which would be pi. Right? Yeah. That's why we do the gateway testing. That's why you take them over and over again, because you can't do these problems, you don't know how to do a derivative. Right? All of chapter 4 is things that involve the derivative. So every one of these things, to do them, we've got to be able to do derivatives. All right, now we're going to plug in a 1. So cosine of pi halves we said was 0. So this whole thing is, so the top's got to stay 0, right? Is that right? Yeah, it's got to. Put a 1 in here, cosine of pi, that's negative 1. Actually, it doesn't matter as long as, well, I guess we got to see if we get 0. Cosine of pi is negative 1 times pi, so this is 0 over negative pi, which would be 0, I guess. There we go. 0 over 0 this time is 0. What else? We did one in the other class that had arctangent in it. Anybody do that one? I thought that was a good one to have to think about. 62. Let's do that one. Limit as x approaches 0. Arctan. Was it just arctan x or arctan 2x over sine 3x? Yeah, again, that's another good one. We've been doing a lot with powers and stuff like that, right? But this really forces you, with powers, you can talk about is the big one getting bigger and high powers dominating, that kind of stuff, and that's a good thing with those. But you can also do L'Hopital's rule. We get into the e to the x's and the sine x's, sometimes cosine x's especially, then you can't do that as much. Now, so on this one we get arctan 0 when we plug it in. And of course we know sine of 0 is 0, but what's arctan 0? It is 0. But now remember, what's that mean, arctan 0? What it means is the solution to this. When is tangent 0? Which is like asking, when is sine over cosine 0? When what? When is sine over cosine 0? When sine is 0, right? Any fraction is 0 if the top is 0. And it can't have the bottom be 0 at the same time. but it wouldn't be there, right? Sine over cosine is 0 when sine is 0. That's something we're going to actually use a lot this year, coming up in chapter 4, is whenever a fraction is 0 is when the top is 0. It's undefined when the bottom is 0. So it's whenever sine is 0. Well, when is sine 0? Well, it's 0. Also at pi and those other things, but remember, we do arctangent, we limit that domain, so we're only going to use 0. So you've got to be able to do that. I mean, on the quiz tomorrow, there could be a problem that has arctangent or arcsine or arccosine. You've got to know those trig values, right? So if I ask you for arctan of 1/2, or excuse me, arcsine of 1/2, remember what that's asking. That's asking when does sine equal 1/2, right? Like pi 6, right? That would be the answer to arcsine 1/2, would be pi 6. So we've got to be able to do those trig values. Okay, so anyway, what that tells us is we get 0 over 0. So we can use L'Hopital's rule. So what's the derivative of arctan? U squared times u prime, right? Times the derivative of 2x, which is 2, right? So sneak in a little gateway practice for those of you who still have to take that, right? Arctan is 1 over 1 plus u squared times u prime. The derivative of the bottom would be cosine 3x, and then kick out a 3 times the derivative inside. Derivative of 3x is 3. Now we put in our 0. 0 squared is 0, plus 1 is 1, 1 over 1 is 1, 1 times 1 is 2. Or excuse me, 1 times 2 is 2. On the bottom, put in 0, cosine 0 is 1, 1 times 3 is 3, 2/3. So again, this would definitely be one you'd have to have some work. Now, you're not going to get an answer of 2/3 here probably without showing some work. Now, I suppose somebody, I can't imagine somebody would do this, but I suppose somebody could look at this and just say, there's a 2, there's a 3. I'll bet the answer is 2/3. I don't know that anybody do that, but I guess if you're really desperate, you might. And that would probably be one that you would not get full credit for. Okay, if you just had 2/3. I don't even know if you deserve any credit.
You deserve extra credit.
My thinking on that would be, yeah, you either just blindly guessed, you looked on your neighbor's paper, or something along those lines. I can't imagine thinking you did anything good to get 2/3 in. All right, so that would be an example. All right. Any others? Any others? There's a lot of them there. 73. Limit as x approaches what? 0 from the right. X squared times natural log x. Did we do this one? We did some natural log in this, didn't we? We didn't do this one yesterday? Huh? In our notes, I mean. We did. That's fine, we'll do it again. This is one of those 0 times infinity. 0 times infinity. Okay? Yeah, this is one that I picked out in the notes. So if you put in a 0, you get 0 squared, which is 0. And then if you do ln x, what you get is negative infinity. Now the reason for that is the natural log graph looks like this. So you can't put in a 0, it's undefined. But from the right, it's going towards negative infinity. So what we have to do, anytime we get 0 times infinity, let's go back to this. Okay, anytime we get 0 times infinity, we have to turn that into one of these two. Right? Now, the way we do that is with a reciprocal. And this technically, again, infinity is not a number, but the reciprocal of 0 is infinity, and the reciprocal of infinity is 0. Because if you think about it, what you're saying is the reciprocal of a really big number is a really small number, and the reciprocal of a really small number is a really big number. So 0 and infinity are like reciprocals. So if you just flip 0 down with its reciprocal, now you've got infinity over infinity. Or if you flip infinity down with its reciprocal, you have 0 over 0. So that's how you turn this into this. So 0 times infinity is not 0, just like 0 over 0 is not 1. Okay? So we go to this, and we got to flip something to the bottom. Probably the easiest thing to do would be to flip the x to the negative 2 down to the bottom. So now what we get is an infinity over an infinity. 0 to the negative 2, or excuse me, that'd be like 1 over x squared, and as you approach 0, as this gets small on the bottom, the fraction gets big. So it's infinity over infinity. So we do L'Hopital's rule, which would be 1 over x, and then we do the derivative negative 2x to the negative 3. Okay? And what I would do here is do some simplifying. So I would flip this up as x cubed, which ends up being x squared on top, negative 2 on the bottom. So now as x approaches 0, you get 0 over negative 2, which would be 0. Okay? There was another one similar to this. I think it had like cotangent in it or something, or tangent, or isn't there one that's got like an x times a tangent, or a, is it number 80 maybe, or yeah, there it is, number 80. Yeah, let's look at number 80. Limit as x approaches pi halves of pi halves minus x times tangent of x. So again, this would be that same situation, because if we look at a tangent graph, tangent comes up like this, and it's got these asymptotes at pi halves, negative pi halves, and so forth. So as x approaches pi halves, tangent's going to infinity, or on this side it's going to negative infinity. Okay, so this is an infinity, and this is a 0. 0 times infinity, we don't know. So we need to do a reciprocal thing. So which one could we flip to the bottom? Tangent could flip to the bottom and be cotangent, right? Now, that would be one option, which would be fine. Matter of fact, let's do it both ways. Let's do it both ways. So one way would be to do pi halves minus x, and then flip the tangent down as cotangent, like that. Okay? So now we're going to get 0 over 0. Right? Cotangent of pi halves is 0. All right? Because it's cosine over sine. All right, now we can do L'Hopital's rule. So the derivative at the top is negative 1. What's the derivative of cotangent? Negative cosecant squared. Now that might be a reason to not do it this way. If you don't know the derivative of cotangent, you might want to avoid this. Okay? It's that. Now, cosecant is a reciprocal of sine. The negatives cancel. So 1 over cosecant squared is the same as sine squared. Right? And now we can plug in our pi halves. What's sine of pi halves? 1 squared is 1. So there we get 1. So again, we started out with 0 times infinity. That is not 0. Turns out in this case it's 1. Okay? Now, the other thing I was thinking of doing was making this pi halves minus x, and then changing the tangent to sine over cosine. Anytime I get a tangent or a cotangent or secant, I'm going to see if maybe it would be better to use sines and cosines. Change those into sines and cosines a lot of times is better. Not always, but a lot of times. That actually wasn't too bad right there, as long as you knew the derivative of cotangent. But if I change this to sine over cosine, now look what happens. I put a pi halves in here, I get 0. Sine of pi halves is 1, so on top I get 0. Cosine of pi halves is 0, so right away I get 0 over 0. Okay, so now I'm ready to do L'Hopital's rule. Now the problem is when I do the derivative at the top, I have to do a product. So the derivative at the top would be negative 1, leave the sign alone, plus pi halves minus x times derivative of sine, which is cosine. So I have to do a product rule. And then the derivative of cosine is negative sine x. Right? Now again, I apologize. I don't apologize really, but I mean I feel for those of you that are still taking the gateway test, because remember, this is not a part of what you have to do on the gateway. We're just doing derivative top, derivative bottom. We're not doing a quotient rule here. Right? That's not part of it. That's a different type of problem. Okay? But anyway, what we do need to do here is when we do the derivative top, we got to do the product rule. All right, now we put our pi halves in. Sine of pi halves is 1, so this would be negative 1. Pi halves minus pi halves is 0, times cosine of pi halves, which is 0, so negative 1 plus 0, that's negative 1. Sine of pi halves is 1 with a negative on it, that's negative 1. Negative 1 divided by negative 1. Sure enough, same answer. So whichever one is easier, kind of depends on whether you'd rather do the derivative of cotangent or you'd rather do a product rule on that other one. Okay? All right, so that's L'Hopital's rule. All right, so back to those limits. Have we done examples of all those things? I guess the only thing we haven't done today, we didn't run into one of those where we have to check both sides, right? X approaches 2, you have to check, 2.01, 1.999, put those in, see what's happening there. But we did some of that yesterday. Anything else? Anything else? Any other limit ones you wanted to see that you tried? Which one? Was there another one? 59? Let's do one more. We'll do one more and then we'll have work time and people can ask about them and you can work together. I got a worksheet with someone. What does it say? X minus sine x. Okay, so you put in a 0, you get 0. Put in a 0 here, you get 0. So 0 over 0. Okay, so derivative of the top is cosine x. Derivative of the bottom is 1 minus cosine x. So now we put in a 0. Cosine of 0 is 1. Cosine of 0, 1. 1 minus 1, a good one. Okay, so now what? Okay, well, that is where, yes, well, that's where the book and your calculator sometimes, like on the video, they say you really shouldn't say limit equals infinity because infinity is not a number, right? So we should say does not exist. But I think what they're saying there is that's why, because it's infinity. But here's what you should do. If this was on our test, you would do this. You would say does not exist, which would be a start. But we just go back to here, right? What did we say if we get something over 0? We check the left and right, okay? And that's what we should do here. So we're going to go x approaches 0 from the left, which would be like negative 0.0001. And x approaches 0 from the right, which would be positive 0.0001. Right? So we're going to put those up here. Now, it's a little harder with cosine to plug numbers in. All we have to do then is think of a cosine graph. Here's a cosine graph. So, if I put a number, an x, a little bit to the left of 0, what is cosine of a little bit less than 0? A little bit less than 1, about 0.99 something. So we would get like 0.99, so we get 1 minus 0.999. That's a small positive. So we get 1 over a small, well actually we get like 0.9999, but the top, remember we said it doesn't matter, it's basically 1. But we're going to get a small positive. So that's going to, I should have put that there. Okay, let's put it. X approaches 0 from the left, we're going to get a small positive, which is infinity. Now let's do 0 from the right. Same thing. From the right, we get a little less than 1, 0.999. 1 minus 0.99 is another small positive. That's a good one, because I'm not sure we've had one. Usually when we do it, 1 is positive infinity, 1 is negative infinity. Well, that's usually because it's a vertical asymptote where they're going opposite directions. Sometimes you get a vertical asymptote where they go up like this, and that's what's happening. So that's the answer I want to see. Okay, but the back just said infinity because that is what's happening on both sides. Okay? That's really good. All right. Well, let's let you work today. Like I said, let me pass out this worksheet. So the worksheet from last Friday when I was gone, it had the matching, it has some matching on it, it has the slope fields on it. If you want to check your answers to that, whatever, that's going to be setting up here. Also, the worksheet we're about to do today has some limit problems and the Newton's law of cooling, and you can come check your answers on that if you want to as you work along. So you can have the rest of the time here to study, work together, get prepared for this quiz tomorrow and whatever else it is you need to get prepared for. And no, the student staff basketball game does not count. It's something you need to get prepared for. Okay, 0, 0, she did the derivative to be 1, and then 1/3 x to the negative 2/3.